problem. I literally just took these. I snipped them from one of the photographs that one of the groups sent me yesterday. I want you to tell me the story of the car's motion. What you got? Who can start us out? Yeah, get us started.
They're going at a pretty constant speed, and then they start slowing down, and then they stop.
Okay. So it looks like they start off with some positive speed, right? Yeah. So they start at some initial velocity. You guys okay today?
Yeah.
We gonna make it? Okay. We're focused to physics. Physics is on. Physics brain is on, right? I know that there's lots of other stuff that goes on in your world, but right now we're physicsing. All right, so we're gonna start off with some initial velocity. And how did you know that it started off with some initial velocity?
Because it's going at diagonal.
Yeah, there's an angle, there's a slope to that line, right? All of those things. That's all true. I love it. So there's an initial velocity because there's some sort of slope here. Is there any way else that you could look at this graph and know that it starts off with an initial velocity? Where else can you look?
At the velocity graph where it starts in the positive and then goes down.
Yeah, for sure. So there's just lots of places to look. So whichever graph you choose to look at, there's a lot to see. There's an initial velocity here. I'm just going to mark that. And actually, friends, I should have mentioned this before, and I forgot. I'm sorry. If you have your gold sheet, remember those gold sheets that we did yesterday or a couple days ago? I mentioned this last period. People thought it was a pretty good idea. On the back of that, you've got some space. If you would like to draw these three graphs, just sketch them out so that you can write this stuff down right now with me. That might not be a poor idea because then you'll have this to reference again. So if you go on the back of your gold sheet, just so that you can sketch them so you can have your position graph, velocity graph, and acceleration graph, and then you can write this stuff down with me right now. Do you have that gold sheet? Do you know what I'm talking about?
The green sheet.
No, the gold one. It looked like, I'll show you.
Oh, yes. We got it.
Like this one,
Yes.
right? Yeah.
I love that.
I know, me too. It's great. It's a good sheet. All right. So if you draw those graphs, then you can notice that there's an initial velocity here. And then we see that velocity is decreasing. So it starts off with some VI, and then the velocity decreases. A less technical way to say that would be that the car does what? It slows down. Yeah. Indeed it does. All right. Tell me more information. What else? What else can you tell me about this graph? Drake, what else do you see from this graph? Other interesting information.
Like about the car or?
Yeah, the car's motion.
Oh,
Yeah.
It's kind of like the velocity decreasing at like a constant rate.
Absolutely it is. That's a good observation. So the velocity decrease section, put it right here, at a constant rate. How do you know that it's decreasing at a constant rate?
Like the velocity versus time graph, it's not like straight.
It's not flat and it's
going down, I guess.
Yeah. And so we can say that we've got a constant slope on the V versus T graph. Nice job by that. That was good. That's awesome. So you can look at the slope. You could also look at the acceleration graph, right? And either one is valid. I'm not saying that this is the wrong. Absolutely, you could be there. Or you could look here. If you look at the acceleration graph, the acceleration is constant the whole time, right? It's a constant negative acceleration. So if you have a constant negative acceleration, that means that you've got the velocity going down, 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 down. Yeah. Anything else? What else can you tell me? There are a couple more pieces of things that would be interesting to note here. Where does it start?
Origin.
Starts at the origin. That's a good thing to know. And does it move in the positive direction or the negative direction? It's in the what? It's in the, oh, sorry.
What graph are we talking about?
I'm saying the object starts at the origin. I want to know if it's moving in a positive direction or a negative direction.
Positive.
And why?
Because it's in the first quadrant.
It's in the first quadrant, like the graph of the position, right?
Yeah.
Yeah. So, and I'm not trying to pick on you. I'm really trying to make sure that when you're describing these graphs, because I've been talking to people about these graphs both in this class and in AP Physics, and a lot of times people just say it. And the word it doesn't tell me what you're talking about. Are you talking about position, velocity, or acceleration, right? So be specific. Don't be lazy about it. It, meaning the position, is always positive. So if it's always positive, that means that it's moving in the positive direction. Away from the origin, right? What do we know about its speed at the end? Dawson, how fast is it going at the end of the story?
This constant.
So the velocity starts here, and then throughout the story, we said that the velocity decreases, which means that it's slowing down, right? We can say that it's got a negative acceleration. I'm asking, what's its velocity at the very end of the story?
Would be 0 because it stopped.
Yeah. Well, so it stopped. You're exactly right, but I want to know how you know that. How do you know that it stopped?
It does, yeah, it doesn't continue on the graph. It just stops at that axis.
So can I ask a question? A follow-up question? What if I had a velocity versus time graph that looked like this? Would that car have stopped at this time?
Yeah.
What do you guys think? If the velocity versus time graph looked like this, at the end of that story, is the car stopped?
It's going to slow velocity.
It's going at a slower velocity, right? But here is what? Let me ask it this way: what does it mean to stop?
Zero.
Zero. What's at zero?
The line, and that's it too. You can just say that's
What value? The position, the velocity, or the acceleration? What's at zero if you stop?
The position.
The velocity's at zero, right? Come on. Shh. Did you say that and I just didn't hear you? Oh, okay.
Good job, Ryan.
Okay. Shh, hold on. I want to ask. What's your question?
If it just stops in the middle of the graph, like how do you know?
How do you know it kept going?
I don't. I don't know anything about it. All I know is that I have this data, and so I'm saying
Like it's going at velocity, but then is it just like disappear?
that's just when we stop taking data. I mean, like you take a video. Let me give you this example, right? So let's say you're taking a video of an object moving. It could be anything, right? It could be a person running a race. It could be a person throwing a ball. It could be whatever, right? Okay, so you're taking a video of an object. When do you stop the video? Whenever you want, right? And so if you're watching and if you're taking a video of a football player who's running downfield, right? And all of a sudden you stop it and they haven't stopped, like there's been no whistle blown, there's no score that's happened, like you just stop the video. Even if that object hasn't, like that's just the end of the story. Does that make sense? It's kind of a weird but not all of them. Like the next one we're gonna do, they haven't stopped. It's just when we stop the story.
Can you like do that in a lab though? Like just stop taking negative before it gets back to zero?
Sure, depending on what your question is.
Okay.
Yeah. I mean, it's a fair question. I appreciate you asking it, right? Yeah. I mean, there was another one that we did on the set that we were just looking at yesterday that looked like this, right? There was one that looked like this, and then another one looked like this. Does that one stop?
So with the
No,
angle
it's just
down
moving.
one, if it
Yeah.
hit that velocity and then just stayed at that velocity, with the line would just flatten out?
The one that we just looked at?
Yeah.
Let me find it. Hold on just a second. Sorry. Here?
No, the one with the bottom.
Oh, I don't know. I mean, I think that's just where the.
No, I know, but I'm saying if it hit the velocity and then decided to keep going at the same velocity, it would just.
Then it would go like that. Is that what you're asking?
Yeah.
Yes. Thank you for clarifying your question. I appreciate that. Sometimes I think I know what you're asking, but I obviously didn't. Yes. Yeah, so in this case, you're going at a constant acceleration, you're slowing down, and then you're just moving at a constant speed. So the detail that I was looking for when I was kind of pulling all this out was that at the end of the story in this picture, right, the final velocity is 0, not 6, or backwards 6. Is this okay? I'm gonna give you one more to look at. This was the more difficult of the most difficult of the 4. So I'm gonna give you just a moment with your table mates to tell the story of this graph. Okay? Tell the story of this scenario. I'll give you just a minute to talk. Go ahead. Let's regroup here. I don't know about you, but the first time I ever saw this graph, it kind of scared me because it looked like there was a lot of kind of weird stuff going on, right? Yeah, maybe not. Maybe you're like, I got this. So curves kind of freak me out sometimes when I'm trying to figure out what's going on. But again, just to make sure that we're all okay here, this is the position graph. Oh, it's frozen. You can't see my little X. There you go. This is the velocity graph. Thank you for telling me. And this is the acceleration graph, all telling the same story. So on your orange sheet, again, if you want to draw this, that would be a great thing to put this position graph next to its velocity graph, next to its acceleration, just to give yourself another example. The more examples you have to look at, the better off you're going to be. This one might look weird, but let's look at the velocity graph. Tell me about what's happening to this with the story. If you look at the velocity graph, go ahead, get us started.
It has a constant increasing, or a constant positive velocity, and then a constant negative velocity, or decreasing velocity.
Yeah. So yeah, and part of this is that we have to be really careful about the words that we use sometimes. So if this was a position graph, then this would be a constant positive velocity and then a constant negative velocity. But since this is a velocity graph, this is a constantly increasing velocity. Are you with me there? It's constantly increasing. So in more simple terms, what does that mean if it's constantly increasing?
The velocity's going faster.
The velocity's going up, it's getting faster. So in this little part of the story right here, okay, the car, the person, the whatever is getting faster. It started at an initial velocity of 0, and it goes up to some speed. We don't know what it is because it's just a sketch. Okay. As it's getting faster, what does that mean about its acceleration? Is it accelerating? AJ says yes. Why do you say yes?
Because it's on the positive value of the acceleration graph.
Yeah, because it shows it, right? Yeah. Remember, acceleration is change in velocity over time. The velocity is changing, and it's changing in the positive direction, like it's getting bigger and bigger. So that means your change in velocity is positive, which means your acceleration is going to be positive as well. So you got a positive acceleration, getting faster and faster and faster. Which means if we look at the position versus time graph, we're looking at this part right here. And if you look at that, I'm going to zoom in here so we can see it. Whoa, that's so big. The slope of this line gets steeper and steeper. Do you see it?
Yeah.
Yeah? Okay. It's going away from the origin. Moving away from the origin. In the positive direction. Okay? Faster and faster and faster. What's the second half? What's the second half of the story? What is it doing? Take a look at this. It's kind of interesting. The second half of that graph is the same as this graph. You see that?
Yep.
The second half, we draw a line like this. This right here is just the same as the one we did before. It's slowing down. It's slowing down to a velocity of what at the end? 0. And we can see that right from this graph. Yeah? It has a negative acceleration because the change in velocity over time is negative. Have you ever experienced this motion graph before? The answer is yes, all the time. In fact, I am almost certain that you experienced this motion graph this morning on the way to school. Let's think about what it means, okay? Whether you were in a car, whether you're on a bus, whether you biked, whatever it was, okay? You start off at a velocity of 0, you accelerate, like you put your foot on the gas of the car, right? You speed up, and then probably it's not a straight shot where you're just going at a constant speed all the way here. Oh wait, and even if it is, you have to slow down when you park, right? So you go faster and faster and faster, and then slower and slower and slower. That's at your red light, that's at the stop sign, that's at school, whatever it is. So really, your graph on your way to school, if it was a straight line, which it may or may not be depending on where you live, I don't know, okay, would look something like this. It's going to go like this, and then like this, and then you're going to speed up again, and then you're going to slow down again, and speed up, and slow down, and at each one of these places right here and right here, that means that you've got, that's like your red light or your stop sign. Making sense? Okay? So this is literally what your motion graph looked like on the way to school. Probably. Okay? If you can think of a reason not, let me know. But that seems to make sense to me. All right. Questions on this before we move on? Next thing on our list of things to do is to look at those green half sheets. So you had that green sheet of quantitative analysis problems. It looked like this. I'll pull it up here so you can see it. It looked like this. Hopefully you've taken the time to do this. I'm going to give you just a couple of minutes with your table mates to compare answers, and then we're going to go around and share out. Okay? Go ahead and go through them with your partner or partners. Issues there? Okay. All right, we're just going to go around table by table and go through. If you have any questions about the answer, then bring them up so we can discuss. Ben, we're going to start with your table over there. On number 1, letter A, it says, is the acceleration greater between 2 and 3 seconds or between 5 and 6 seconds? What'd you guys say? Between 5 and 6 seconds. And the other piece of this that you may or may not have written down before is the why. And I'm going to ask that, and I would encourage you to write it down because it's a great thing to look at, again, when you're studying, when you're trying to get all that stuff put in your brain. Why did you guys say 5 and 6?
Steeper slope.
Steeper slope, yes. We pay attention. We know that it's a velocity versus time graph. We're looking for acceleration. Acceleration is found by the slope of a velocity versus time graph. Awesome. All right, my friends. Letter B says, during what time interval is the acceleration 0?
3 to 5.
3 to 5 seconds. And why did you say 3 to 5 seconds?
Because the velocity is 0, which means the acceleration is this.
The velocity is 0? I think
No,
it's
wait,
down here.
I'm wrong.
No, you're not. You're not totally wrong. I think you just missed one word. So you're saying between 3 to 5 seconds. Yeah. Okay. Yep. So you say the change in velocity is 0. Yep. So the velocity is constant. We're just going to write this down. And I'm not trying to pick on you. I just want to make sure that we're using really good words here. So we're going to say that the change in velocity is equal to 0, which means that the acceleration is 0. Nice job. All right. We're going to skip C and E. We'll come back to them next week. We're just not quite there yet. So we're going to go back, or we're going to go down to D. And question D, what is the acceleration between 5 and 6 seconds? You said 5. 5 what? So that's a really good question, Miss Kay. There's something, and we have not talked about this. So this is an opportunity right now, friends, for you to pay really close attention because I'm going to tell you something new that we haven't talked about yet. So paying attention right now. Here it comes. So let me ask, where did you get that 5 from? The number is right. Yeah, so you're looking at between 5 and 6 seconds. So that's this little section right here, right? And you said that it went from 10 meters per second to 15 meters per second. So that's the change in velocity. And we need the time as well. Remember we said that acceleration is change in velocity over time, right? And so really, what was she finding? The what of the line?
Slope.
It's the slope of the line. It totally is. That's where that 5 comes from. Given this, I want to look at the units. This is the thing I wanted to make sure you were listening for. The units of meters per second on the top. The units for time are seconds. So the units, we haven't really defined this before. The units of acceleration are meters per second per second. That's a lot of weird stuff to say. Do you agree? Yeah? Yeah? We can actually write this out if you want. This seconds that's right here in the denominator of the numerator goes down to the denominator. So really what you get is meters per second squared. So if it makes you happy to say meters per second, go for it. I usually say meters per second squared. So that would be like the big takeaway moment right there. It was great. All right, we're going to go back to number 2. So you're flipping it over to the back. We're going to stay in the back there. So Anna, Erica, Alex, what'd you guys get for? So this, I have to pay close attention here. This is a displacement versus time graph. It's different, isn't it? We have to make sure to remember that and pay attention to what kind of graph we have. What is the velocity between 20 and 25 seconds? What'd you guys say? 0 meters per second. How did you get that? Yeah. So between 20 and 25 seconds, that's up here, right? There's no change in position, which means that there's no velocity. Yeah. Okay. You can say the slope is 0. That's another way to say that. All right. My last back table. Is the velocity greater between 0 and 5 seconds? Or between 10 and 12 seconds? What do we say?
I don't know that one.
Don't know this one? Do you guys have it back there or no? Dawson looks really excited to tell us.
Go for it, Dawson.
Go, Dawson. What you got?
10, 12.
10 to 12. Why?
Steeper slope.
Steeper slope. Nice job. Yeah, that's what it is. When we're looking for the velocity from a displacement or position versus time graph, we always look at the slope. The velocity between 0 and 5 seconds, the slope here looks like this. The slope between 10 and 12 looks like that. That would be a steeper slope. Nicely done.
Thank you.
All right. I'm going to stay at my back table. What is the velocity between 15 and 20 seconds? Did you guys get that one?
I got
What'd you get?
3/5 meters per second.
3/5 meters per second. Do you know how I feel about fractions? They're not my favorite. It's okay. No judgment. Let's put this into decimal form. Is that okay? Can we do that?
0.6.
0.6 meters per second. Do we agree with that number? Everybody good with that? The velocity between 15 and 20 seconds. Hold on just a second. I just want to make sure that I agree with this. Between 15, so here's 15 seconds, and here's 20 seconds. So this is my rise. This is my run. So the run is 5 seconds. We all agree with that? And what is the rise?
9.
What's that?
9.
9. Got to look at the scale, right? And that's just something I wanted to make sure that we saw. So it's 5 seconds this way, but each of these boxes is actually worth 3 meters. 3 meters. So it's actually a rise of 9 meters in 5 seconds. So I'm going to change that to a 9 and change this to 1.8. But your process was right. And so if you were doing this on a quiz or a test, and if you just wrote 3/5, I'd be like, ooh, that's too bad. But if you showed me this process, and you just happen to have a 3 here, and you had a 5 here, I'd be like, okay, I can see where that came from. Probably you're not going to get a perfect on that, right? But you're going to get like a 7, right? Because you've shown me that you know stuff. didn't look at the scale. That's what I'm saying. We're not going to talk about that right now. All right, let's do D. Letter D. I'm looking at my table right here, my back L table. During what time interval does the object accelerate? What you guys say? What's that?
Oh, wait. I thought we were on E.
Nope, we're on D. Sorry.
0 to 12 seconds.
0 to 12 seconds. Why do you say 0 to 12 seconds?
Because it's like this change is like getting faster.
Yeah. Yeah, so there's a change in slope, right? It's a curve. Means a change in slope, which means a change in velocity, which means that there's some acceleration. Yeah, it's curved. Absolutely. And then finally, I'm going to come right here. Letter E. What is the displacement between 15 and 20 seconds? 9 meters. Where'd you get that from?
I looked at the graph.
Yeah. This one's kind of funny because you don't have to do anything with it. You just have to count, right? You do have to realize that these are each worth 3. But besides that, that's it. That's it. Okay. How are we doing on this? I feel like having gone through it, people are feeling okay. But I know that not everybody responded. So if you're one of the people that didn't actually say anything, maybe that's just because you were deferring to somebody else. But if you don't understand this, you need to take that on as your responsibility to figure out what's going on. Okay? We were going to do homework questions today, but just because of time, I want to make sure that we're moving on. I am going to make a Google form that you can let me know if you have homework questions so we can make that a more efficient process. So I'll let you know about that on Monday, okay? Right now, we are going to get into, we're going to get into lab groups in a couple minutes. We're going to get started. I'm going to talk you through what this lab is so that you're aware of it before we get too far in. Okay, hey Alex, can you grab me one of those long skinny boxes that are back there? The long skinny, so all right, so the lab that we're going to do today allows us to actually make displacement and velocity versus time graphs, okay? It uses this thing called a motion detector. And a motion detector sends out a sonar signal. Sonar is just a sound wave, okay? And it uses basically the same technology that a bat or a dolphin uses when they're trying to navigate, okay? So it sends out a sound pulse, and then that sound pulse bounces off of whatever it sees or whatever it comes into contact with and bounces back. And based on that, it can calculate how far something is and how fast it's moving, okay? It's a pretty cool little piece of technology. So you're going to use this. A couple of things about them. If they fall, if they drop, they will break. And they are not inexpensive. Okay? And I will hold your lab group accountable. Okay? So you need to make sure that you're careful with them. All right? That's the first thing you need to know. So the game is that you're going to set this up, and I'll show you how to set it up. You're going to move relative to the motion detector so that you produce a graph that closely approximates the graphs that are shown. So when you're doing that, it will bounce off of your clothing, but because your clothing isn't completely flat, it sometimes comes up with bad data. So I'm going to have you grab a whiteboard, and you'll hold the whiteboard in front of you, and then it'll get a much better signal. Okay? So I just want to let you know that. You're going to write down a description of how you moved. Okay? And then also draw the other graph that is missing. So in the first few, it's the velocity graph that's missing, and in the last couple, it's the position graph that's missing. Okay? We're going to go ahead and count off, and then I will talk you through how we're going to get started. So we're going to count off by 13s. So this is what you're going to do. So listen carefully. This is not a hard lab to do, as long as you listen carefully right now, okay? You will need one Chromebook, a motion detector that comes in the long skinny box and has a cord that has some white some white things on the ends, okay? And a LabQuest, which is the flat box with a USB cord in it. I see as I'm opening this one that this one got appropriated, which is really frustrating to me. You'll see over here in this green box that it says, when you're finished with the lab, please be sure to put all of the equipment back just as you found it, okay? All of the boxes do close and they don't need to break. You need to put things in patiently and make it work, okay? You understand what I'm saying? Please be careful. So you're gonna get a motion detector box and a LabQuest box. You'll also need to get a whiteboard and the pink lab sheet. So it might make sense for you to divide and conquer. Send somebody up to get a whiteboard and pink sheet, and then the other person to go get that. On your Chromebook, you're going to search, just go into Google and search for graphical analysis Chrome, okay? And that will bring up a plugin that you're going to install and open. All of the cords just kind of connect together nicely. The motion detector connects to the LabQuest. The LabQuest connects to the Chromebook. Okay? Go ahead and get started on this. Everybody take one. Each person needs a sheet. One whiteboard per group.
Maddie, how do you got a sheet?